lower bound for worst case of comparison searches. Yeah, you know, all this comparison searches. Okay, yeah. All right. From our part B.4, we know how powerful this decision tree tool is. Here, let us apply it another time, so we can find a lower bound for comparison searches. Another good topic. All right. Draw a decision tree for a comparison search. We want to draw a general decision tree here, just like we drew a general decision tree for a comparison sort. No. But here we put an important restriction: comparison-based algorithm. Don't forget this, comparison-based algorithms. Otherwise, you will get the wrong conclusion. Comparison-based. Okay? So before we go to next, let me give you those search algorithms that do not belong to this category. Index search does not belong to index search. We do not do comparison. Yeah. Hashing does not belong to this. Hashing. We do not do order-based comparison. More specifically, we do matching. Yeah, for hashing, we do matching type comparison, right? Not order type comparison. So that's different. Here, because this comparison based means order type comparison, not matching type. Yeah, so that's why that kind of details important. Yeah, do not get confused. Yeah. Next. All right. Now, let's look at the decision part. A typical node in the decision tree for the binary search. Yeah, so let's, look at the double binary search, for example, as an example. Because we understand the binary search well, so we use that as an example. Then later we can go to, any search, any comparison search. Yeah. Yeah, for a binary search, so typically, so we compare, so then we, go one side, then the other side. Yeah. And when we do the comparison at the node, there is a value. If equal, then we stop, we return the element. So we find it. Yeah. So that's binary. If not equal, we have two outcomes. So here you can see at the node already contains one decision. The node has a decision. Okay? Yeah. So the node has an outcome. The node itself has an outcome. So different from the sort. The internal node does not have any outcome. But for the search, comparison search, the node itself contains an outcome, equal type outcome. Okay? Then, other than this node outcome, there are two other unequal outcomes. So that's why we also have two branches from the node. Yeah. So it's still a binary tree, full binary tree. You can see full binary tree. Okay? So that's the basic structure of the decision tree of, comparison search. Here, I give you example, the decision tree example for the binary search for 10 elements. Here we have 10 elements. It looks like this. How do you get that? It's very simple. So let me show you. Yeah. How do I get this? Right. Suppose we have an array with 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements. Now let's apply the standard binary search on this 10-element array. We assume it is already sorted, so we can do the binary search. All right. First, we compare the key with the element in the middle, and based on our assumption, we compare it with the left median. So that's 5. So that's why we put a 5 at the root. Okay? So less than, greater than case. For the less than, we go to this subarray. Then we compare the key with the left median another time. That's why the 2 here. Okay? So less than, greater than. Okay? Less than, all the number, yeah, we compare with 1. Greater than, so 3 and 4, we compare the left median, so that's 3. Okay, so then 4, yeah. Because 3, there is nothing left, right? So nothing left, yeah. Something empty here, okay? Yeah, empty here, yeah. So then right, yeah. And similarly, greater than 5 elements, we compare the one in the middle. So that's why we put 8 here. Okay. Then less than 8, 6 and 7, we compare with 6 first. Okay. And 8. Yeah. Nothing here. Okay. All right. Greater than 8, 9 and 10. So we compare with 9 first. Yeah. So less than, yeah. So you can see we get a decision tree like that. Okay, yeah, for the binary search. Yeah. So here you get the idea. We can always draw a decision tree for a comparison search. Yeah, not necessarily binary search, any comparison search. Yeah. All right. So I explained the, how do we get that? Yeah. What is the relationship between the height and the size? Yeah, so we know height, the meaning of height, the worst case efficiency. Yeah. All right. Decision tree for a general comparison search. Now we consider a general decision tree. Okay. Yeah. Assume it looks like this. Yeah. Given a comparison search, we have an ordinary binary tree. So this is an ordinary binary tree. So it is not a full binary tree, okay? Because not full, right? So this one is missing, okay? Not a full binary tree. This branch missing, okay? Ordinary. But even ordinary, remember, some of the results for full binary trees we still have for ordinary binary trees. Not necessarily a full binary tree. We know that. Look at here. Yeah. No need to consider internal and external nodes. Yeah. So we do not need to separate internal, external. So they have the same status. So not like sorting, comparison, sort. The status different. Internal, external. Here the status internal, external the same. Yeah. All right. The height corresponds to the worst case efficiency. Yeah. This argument is still true. This statement is still true. Okay. All right. So what is the relationship between height and size? So we need to derive this relationship to give us the lower bound. Yeah. So the relationship. Yeah. Actually, we use the similar way we got in the part B.4. Yeah. The procedure is almost the same. Derive the inequality. Height, we know the meaning of the height. Okay? Yeah. And for this general binary tree, the height h, we can look at the number of nodes at each level. Yeah, we did that last time, remember? Yeah, the same as what we did in B.4. Yeah. Okay, yeah. All right. So the number of comparisons for the worst case, we know h plus 1. Because at the root, you do one comparison. At each level, you do one comparison, right? From 0 to h, you do h plus 1 comparisons. Okay? All right, so the total nodes you have, that's n, right? So you add up all these numbers from all levels, you get 2 to the h plus 1 minus 1. Okay? Yeah. So from this inequality, you can get the lower bound easily, right? Yeah. So we have, for this general comparison search, yeah, the number of comparisons, this number for the worst case, yeah. Total number of nodes, we have this inequality, yeah. So we can solve the inequality using log base 2, okay? And this number is an integer, so we take the seeding function. See? Yeah. All right? That gave us the conclusion. So for any comparison search, a lower bound of the worst case performance is this expression. Okay? And for binary search, actually we achieve this lower bound. So it's possible to get this lower bound for a particular search, comparison search. That is the binary search. This means the binary search is optimal. So we prove the binary search is optimal among all the comparison searches. Do not drop that comparison. Otherwise, it won't be true. Okay? So among all the comparison searches, the binary search is optimal because it reaches this lower bound. Okay? All right. So that's the whole thing for this lesson. And we complete lecture 10. Yeah. So next we will start lecture 11. Yeah. All right. Yeah.